especially for resolutions of modules, but in the definition I don't assume anything. So, and the maps I'm going to call D with a lower index n plus 1, and well, the index is the same as the source of this map. It's one of the conventions. And if I don't want to present this whole information, just for shortness, I'm going to write something like C with a lower dot. So C with a and what's complex is one important requirement that if you consider a composition of any two such maps, so let me say that the maps D n, where n is any integer, are called differentials of the complex. And the important requirement is that when you consider composition of two differentials, then this composition has to be 0. This is one of the requirements of being a complex. And sometimes, usually people understand what indices you're supposed to use. Just for shortness, people write something like d squared is equal to 0 and call D differential. Well, there is a kind of dual part, so let me call this 1 prime. We can define a cochain complex. And I need to say all the same words. I don't want to repeat this. This is kind of silly. But what you need to change is just the directions of all the differentials in this situation. And for the chain complexes, usually people use upper indices. So for the chain complexes, people use low indices. For the cochain complexes, people use upper indices. So if I want a cochain complex, well, I have Cn minus 1 differential with the upper index n minus 1. This hits to the Cn, then there is differential dn, etc. And again, there is a requirement that d squared is equal to 0. So from theoretical point of view, there is no much difference between these two definitions. Well, you can kind of just all the time you can kind of, instead of the index n, you can consider the index minus n. And this, and if you start with the cochain complex, you get the chain complex the other way around. So theoretical doesn't mean too much, but it's important in the applications. In the applications, sometimes two complexes come, well, we can just see that this is naturally a cochain complex. Like, for example, differential forms on the manifold. This is a cochain complex. Or, I don't know, if you try to compute homology of some topological space, if this is homology, this will be a chain complex. If this is cohomology, this is cochain complex. So it's important in the examples. Okay, so the second part of the definition, we can introduce cycles of a complex. So cycles by definition, so notation is Z with the index n. Well, that depends on the complex. So yeah. So since there's no difference between chain and cochain, I'm going to, for the rest of this definition, assume that I work with the chain complex. For the cochain, it will be the same. So if I want cycles of a chain complex, this is just by definition the kernel of the differential. And so at this position, we have differential dn. There's some kernel. This is Zn. This is submodule in the Cn. And there are boundaries. So this terminology comes from algebraic topology, but from the formal algebraic point of view, there is no kind of there is no reason to think about this topologically. Just formal words. Cycles are kernels, and boundaries are the images of the previous differential. So Bn for boundaries of a complex C with a lower dot. This is the image of the differential with the index n plus 1. So these are two submodules inside Cn. And clearly, well, we can see that, for example, Bn is always the submodule in the Zn. Right? Why this is so? Yeah, because d squared is 0. Hence, we can introduce the notion of the homology. So homology of the chain complex. So I'm going to use notation h of n for the complex C. Well, this is kind of the measure how much the cycles are larger than the boundaries, so quotient of the cycles by the boundaries. Okay, so 3. So chain CH, well, since I work with the left modulus, I need to write something like mod R. Right, so this is the category of all complexes or in this case left R modules. But as I was mentioning in the beginning, well, it's not necessary to work with the left complex. We can develop this theory for any abelian category. We take abelian category, consider complexes of abelian category, get a new category of the chain complex of our abelian category. But, well, if you want to really prove something, you need to work much harder, and I'm just afraid we don't have enough time to develop all the steps for any abelian category. But all the essential parts are already contained in the category of R modules. And also there is a, maybe I didn't mention this before, there is a Freyt-Mitchell embedding theorem that essentially is saying that if you consider a small category, which is abelian category, this is a subcategory in the category of R modules, where you can construct some ring R, which is kind of complicated, huge ring, but nevertheless, theoretically, it's thinking about abelian categories. It's not very far from thinking about subcategories of the categories of R modules. Okay, so here we can form a new category. So the category of all complexes. Well, the objects are complexes, and the maps we can define as follows. So let's say CH mod R. If I want to understand the maps between two complexes C and C prime, well, this is just by definition maps. Well, actually, this is the whole family of maps. So this is family UN parameterized by some integer number n from the Cn to the Cn prime. And the requirement is that if you take the d prime n un is equal to the un minus 1 dn. So that's the definition, but well, it's maybe easier to understand if you have a picture. So we have Cn, here we have differential dn Cn plus minus 1. So the differential, the chain complex, decrease the index. So Cn plus 1, dn plus 1. So here there is another complex that has everything the same but with the primes. And the map is just so un plus 1, un minus 1. So the map of the chain complex is just this family of maps. So infinite family of maps if the complexes are unbounded for any integer n. And this last condition that I wrote as an equation, well, it just means that every square that you see on this diagram is commutative, right? For example, here dn un minus 1, so it's going like this, and then we have un and dn prime. So every square is commutative. So that's the definition of a category of chain complexes, and I'm going to leave this as a little exercise, which is very easy, I think. We can show that the category of the chain complexes is abelian category. Just formally checking all the conditions in the definition of the abelian category. In this case, it's not very hard. Okay, so next part of the definition 4. Well, here, as you can see, we consider the maps of the complexes which are kind of degree 0. They preserve the degree. But potentially you can also consider maps that goes, for example, from Cn to the Cn minus 1, so changing the degree. Or you can go to the 2 steps, 3 steps, etc. This is not the maps in the category by this definition, because maps in the category are all of degree 0. But you can introduce this notion of the home with a bullet, as this indicates that this home is another complex. So between two complexes, C with the bullet and C prime with the bullet. And this is by definition, this is a product of the home D, C, C prime. So home D stands for the maps of complexes of degree D. So D here is any integer. So home, let me write this, home D between complex C to the complex C prime. Well, this is just, as I said, all the family of maps UN. Well, UN is a map from the Cn to the Cn plus D. So here, these are just the maps that increase the degree by D. Okay, so at the moment, the way we just define this thing, this is just an abelian group, right? To say that this is a complex, we need also introduce the differential. Well, actually, no, not just an abelian group, this is a graded abelian group. And on this graded abelian group, I introduced the differential. I'm going to call this capital D with the index n. So this will be. Разные, да, я про это и говорил. Что?
Ну вот там чейн, категории правых.
Левых.
Ну, а зачем? То есть на что это влияет?
Левых или правых?
Ну, в смысле, вот у нас чейн категории правых модулей. Почему правых модулей?
Да, я обозначение неправильно использовал, надо было R с другой стороны написать. Ну, не знаю, что здесь легче исправить, давайте будет правых. Про правых или левых ни на что не влияет. Ну, кольцо произвольное, можно перейти к противоположному кольцу.
Там право.
Не, это я перепутал обозначение, нет. Okay, so the differential on this graded abelian group. So dn, this is will be from the home n, still some complexes C and C prime, to the home n minus 1, C and C prime. So by definition, if I want to compute this differential on some map F, then I take post-composition with the differential D prime of the map F minus, so there is a correct sign, minus 1 to the n, and then the composition of the F and differential D. So that's the definition of this differential. And I'm going to again leave this as an exercise that the D squared is 0. I just need to plug in one formula into another to do this exercise. It's very easy. So, and with this thing we can say that home. Well, yeah, you need to look at the corresponding indices. Yeah, so well, you get this kind of two complexes. You choose a differential. It will hit somewhere on where it's hitting on the target. You apply f, right? This will be this term with the correct sign, and then there will be another term. Yeah. So this f also potentially have an index. Well, I just don't want to write another diagram like this, but it's of the same kind. Yeah. So all these things together give us a complex. So is a complex of abelian groups. And now in particular we can look at this, for example, cycles and homology. So 0 cycles, so this complex. can you tell me what are the zero cycles here? This will be the kernel of this differential, right? Что такое тождественная группа вообще? Нулевая? Нет. Well, if you consider cycles of degree 0, right? These are maps of degree 0. So these are maps that preserving the degree. And initially this is in the kernel of this dn, d0 actually. If this is in the kernel, it means that exactly that the map of degree 0 is commuting with the differential. So what we get is actually the maps in the category of complexes. So this thing can be identified with the maps in the category of complexes. So these are degree 0 maps commuting with the differential. Почему что? Вот это изоморфизм? Well, you take this complex, right? Now you want cycles in degree 0. So you consider home 0 here. So home 0, these are maps that preserving the degree. Precisely as we require here, right? So these are maps preserving the degree. Now there is a condition that since these are cycles, they are in the kernel of this large differential D. But if this is, well, n is equal to 0, if d of f is equal to 0, then this equation is just saying that this f is commuting with the differential in the same sense that we have in this definition. Well, the only difference is that here have u and there have f in the formula. So from this home complex, by the way, there is a kind of special terminology for this. This is home with a bullet, sometimes also called the home complex. This is how we're going to call this. So this home complex, well, at least for the zero cycles, we have some interpretation, but actually it's much more interesting to look at the zeros homology. So H0 of the home, so C prime. Well, since this is homology, well, we're supposed to take cycles and take quotient by something. Well, I can write this as we take the maps in the complexes over right modules, and then take, well, quotient, well, introduce some equivalence relation, right? So this will be chain maps up to some equivalence. Well, there is a quotient category, definitely. There are even two non-equivalent definitions, but here I just meant the abelian group. Yeah, sorry, I forgot the arguments. So this is just the abelian group. Yeah, this is a quotient of the abelian group by some abelian subgroup. But since this equivalence relation is important, let's spend a couple of minutes to discuss this. So what it means that F is equivalent to G. So this means, well, the difference is supposed to be in the boundary, right? So, is a boundary. So F minus G is a boundary. So this is D prime H plus HD, where the degree of the H is -1. Right, so this is what we just get from the definition. Now, in this case, this map of degree -1, so H is called a homotopy between F and G. I think it will be better if I draw another picture. So I have Cn plus 1, Cn, Cn minus 1. So here we have two maps. So Fn minus 1, Gn minus 1, Fn, Gn, sorry, plus 1, plus 1. So now this is Fn minus 1, Gn minus 1, right? And then there is one more map of degree minus 1. So instead of preserving degree, it's decreasing degree by minus 1. So this is Hn. And for example, here the component is Hn plus 1. And now, well, with this kind of more detailed picture, we can right now formula with more details. Fn minus Gn is the same thing. Well, this difference between two maps is supposed to be, I first apply Hn. No, sorry. Is this even? Sorry, this, I think this has to be a plus 1. When I was thinking about this, I was thinking about cochain complexes, but for the chain complex, we need to go like this. This is Hn, and this is Hn minus 1. So differential. So this difference between Fn and Gn, so now we can take dn and then apply to the dn Hn minus 1. This is the second term, and the first term we first apply Hn and then apply the differential. So this is d prime with the index n plus 1. So this is Hn d prime the index n plus 1. So this is how you can see homotopy between two chain maps on the picture, and also this picture is helpful to check that the degree of H is correct. But because otherwise this equation doesn't make sense. It also follows from the definition of the home complex. The degree will be minus 1 for the cochain situation. For the chain situation, this is plus 1. Okay, so that's the homotopy. And then, so this I think was part 4 of the definition. Now 5. We can also introduce the shift functor. So we can shift the complex by some integer k. Здесь? Ну, потому что там минус единица в степени минус, а там n равно единице. Ну, да, единица, соответственно, минус, плюс.
А n не 0 раз? N разве не 0 раз?
Нет. Здесь же написано степень h 1. Значит, здесь же у нас стоит, соответственно, как раз степень этого отображения.
А вот тут D, по-моему, там где-то. Вот тут D, по-моему, там где, который теперь.
Не очень понимаю вопрос.
То есть, откуда вот этот минус?
Как в определении который?
Ну нет, вот так, который стал плюс.
Он вырос из того, что степень h у нас плюс 1.
Ну да.
Да. Ну, здесь стоит как бы разность, но как бы это обычный, грубо говоря, коммутатор двух отображений, но он градуированный. Соответственно, мы переставляем местами отображения там, степени n и отображение степени 1. Соответственно, мы должны поменять знак. Это называется кашулио соглашение о знаках. Ну, соответственно, если здесь это имеет степень 1, значит у меня здесь стоит минус умножить на минус 1 в степени 1. То есть в итоге плюс.
Ну, это
А, откуда вот это равенство взялось? Нет, так это просто по этому самому, по определению. Мы же считаем нулевые гомологии. Да? То есть мы должны взять циклы. Циклы мы уже знаем, что такое. Соответственно, после этого мы должны факторизовать их по нулевым границам. Да? То есть, соответственно, вот это отношение эквивалентности, это означает, что вот это два отображения эквивалента, это означает, что их разность попадает в границы. Ну, соответственно, я и пишу, что разность это какая-то граница. То есть это образ предыдущего дифференциала. А дифференциал вот такой. Okay, so the shift functor, this is easy to define. Well, you just take a complex, and the shift functor, well, here I'm writing for any integer k, so in the notation k is any integer, but of course it's enough to understand what's going on when k is equal to 1. So you just take a complex and you can shift this on one position on the left or one position on the right. So that's the shift functor depending on the sign of this integer k. So for the objects, if you shift the complex, look at the component A, this will be component N, this will be Cn plus K. This is just by definition for the objects in the complex. And for the differential, it's almost the same differential, but up to a sign. So differential shifted by K, and this is minus 1 to the K, multiplied by the previous differential. So this is how this functor is working on the objects, and we also need to define this on the maps, which is again easy if you take a map. So again, I'm going to call the chain map U, shift this by K, look at the component with index N. This is just the components U.
Это хорошо, не вопрос по второй. У нас там минус 1 в карте dn, не dn плюс карта никакой.
Сейчас.
У нас там просто все сдвинулось.
Да-да-да, n плюс k.
То есть это мы просто берем, сдвигаем все индексы на k, параллельно подвигаем минус 1 в нужную степень. Да,
то есть просто натуральный сдвиг комплекса влево или вправо, в зависимости от знака k. Но надо еще подкрутить знаки дифференциалов. Да, это функтор, это называется функтор сдвига. So this thing. Well, this is just a tradition because it's kind of weird to write it the other way around. Right? If you write something like this, well, if you apply a functor to a complex, well, as a functor this makes sense, but the tradition is to write this on the right. You think about this: you take a complex and shift it by 1. Yeah, and this sign is just a convention. I think you can also give a definition without sign, but then you get some signs into other formulas, so it's not really important.
То есть этого знака у него нет никакой концептуальной, просто соглашение, которое потом будет удобно.
Да.
Ага, хорошо, это уже вопрос возник.
Yeah, and for example, using this shift, you can write something like the home with the index k between two complexes. Well, I think for the... just let me finish the formula. So this will be the same thing as the maps. Let me just write with the home 0. This is a map preserving the degree, and then C prime shifted by minus k. So to check this is exercise. Well, I'm not completely sure that this is supposed to be minus k, but so please check this. I think this is minus k, but this needs to be checked. Yeah, so what was the question? Это я отвечал на вопрос, почему вот это функтор, если это функтор, то надо писать, как бы вот функтор применяется к объекту, да? Да, оно просто... Да, а соглашение, что мы пишем этот сдвиг справа. Ну. Окей. And the last part of this definition, part 6. So suppose we have a chain map. By the way, I didn't write this on the blackboard, but the chain map is just a map of chain complexes by definition. So we have a chain map U from one complex into another complex, right? So this means that maybe since I put this bullet on the complexes, it also makes sense to write this bullet for the chain map, meaning that we have this whole family parameterized by integer numbers of maps Un from the Cn to the Cn prime, such that they commute with the differential. And this condition that they commute with the differential means that, for example, if you apply this to the cycles, then you get cycles in the target complex. So chain map is preserving cycles. Well, this is quite easy to check, I think, right? So if something was in the cycles, right? So suppose we have some x that lives in the cycles of the C. And since this is in the cycles, it means that the differential dn applied to the x is 0, right? But now, if I just apply un to this equation, dn of x is equal to 0, and use the condition that differential is commuting with the chain map, I'll get the dn, so dn prime un x is equal to 0. And this has to be un minus 1. Right? So because this is was a condition in the definition that this composition is the same as this composition. So this thing is preserving cycles, and also it's preserving the boundaries. So un you apply to the boundaries of a complex, then you get some boundaries in the complex with the prime b n. The proof is more or less the same. Okay, so we can induce maps on the boundaries on the cycle. So I'm going to call this z of u, and this will be the map from the cycles in the first complex to the cycles in the second complex. And also there is map b of u on the boundaries. And since the cycles and the boundaries are preserved, we can also induce a map on the homology. So, and finally, U is called quasi-isomorphism. B. So map U is called quasi-isomorphism if the map induced on the homology is an isomorphism. And this finishes all the abstract definitions about complexes that we need. Or maybe, actually, there is one more thing that I can say. So this is 7. A complex is called exact, and also you can say that the complex is acyclic. This is the same thing. at least in this course, if all the homology of the complex are 0. And such complexes are also called exact sequences. Well, the exact sequence is precisely the same thing as the cyclic complex or exact complex. That's all the same. And there are examples of this situation which are quite elementary. For example, you can look at the complex like this. Say we have two modules, and I'm saying that this is exact. So let me call this map between modules I. So I have three terms, 0, some module, and another module. I'm saying this is exact. What it means in more naive terms? Yeah, so this just means that M prime is a submodule in the M, right? Because what would be exactness at this term? It means that the kernel of this differential is precisely as the image of this map. So the image of this map is 0, so the kernel of I is 0. So this is a monomorphism, so M prime is just a submodule in the M. So it's exact, it's equivalent to saying that I is mono. And dually, you can write M double prime 0, and this is exact, means precisely, if I call this map, say, pi, this means exactly that the pi is epi. So this is just simple exercises into what exactness means. And maybe another definition, a short exact sequence. For shortness, I'm going to write this SES, short exact sequence. So is да, это же модули. So short exact sequence is just a sequence, is exact complex. Oh, I think terminologically it's better to say exact sequence or a cyclic complex. So I'm going to write a cyclic complex 0 M prime M double prime. That's a short exact sequence. And you can see that this means that if again I'm going to call these maps I and P, so it means that I is mono as before, and also M double prime is the same thing as the kernel of I, pi is epi, and M prime is the kernel of pi. So this is what it means to have an exact sequence. So exact sequences are very important in this homological algebra, well, because we never have any exact sequence, not necessarily the sequence with three non-zero terms. You can always separate any exact sequence into just several such short exact sequences. So we're going to do this several times during the course and in the exercises. So we're going to see why such short exact sequences are important. But at the moment maybe I want to use another blackboard. I want to formulate the snake lemma and prove it. This will be our first statement about homological algebra, but this is kind of elementary statement. It doesn't require too much about complexes. So lemma snake lemma. It says the following. So suppose I have a diagram. So given a diagram, so in this diagram I have two almost exact sequences. There is just on the top row there is an exactness missing on the left, so we only know exactness at these two terms and don't know anything about this exactness at the term m prime, so this is why I don't want to write 0 here. And so let me call maps maybe u with the upper bar and v with the upper bar, and then another sequence like this. But now, yeah, I don't want to require exactness on the right, only on the left. And there are maps. So this is map f prime, map f, and map f double prime. So this is what is given to me. So given such diagram, the conclusion is, so given a diagram of modules, well, maybe it will be better if I continue to draw something on this diagram. So this is diagram of modules, and then we have, so then there is exact sequence that starts with the kernel of the f prime. This is mapped to the kernel of the f. This is mapped to the kernel of the f double prime. Then there is a map that maps kernel of the f double prime to the co-kernel of the f prime. This is mapped to the co-kernel of the f, and this is mapped to the co-kernel of the f double prime. So that's the statement of the snake lemma. And the snake lemma has additional part. So moreover, if u with the upper bar is injective or mono, то там же здесь штрих, без штриха и два штриха. So if u with the upper bar is mono, so then the first map is injective. Oh, again, mono. And if we underlined this map is epi, then the last map is epi. So you can add additionally 0 here in the beginning if you know that you can put additionally 0 here. So for example, if these two things are just short exact sequences, then you have additional 0 here and additional 0 here for the last map. And why this is called a snake lemma? Well, that is because, let me erase the title. We can present this data on this diagram, and people say that this looks like a snake. So here there is a kernel of f prime. This is submodule here. There is a kernel f, which is here. This kernel of the f double prime here. So this maps are just the inclusions of the submodules. All the vertical maps are inclusion of the kernels. And of course, if I have a map, right, so any map is in, since this is a commutative square, any map here is inducing a map on the kernels, and the same here, using commutativity of the square. So then there are corresponding maps for the co-kernels. So there is co-kernel f, co-kernel of the f prime, co-kernel of f, and co-kernel of the f double prime. And again, using commutativity, we can say that there are induced maps on the co-kernels. So finally, this lemma is saying that there is a connecting map that goes like this. So this is usually called map delta. So these three kernels connected via map delta with these three co-kernels is exactly the same exact sequence that we have in the statement. So that's the statement of the snake lemma. Well, the proof of the snake lemma is the first example, what is called a diagram chase. So I don't want to write anything on the blackboard, I just want to show you how you do this diagram chase. Now, of course, the maps on the kernels and the maps on the kernels we get automatically, so the only non-trivial part is getting this connecting homomorphism delta. Well, how you do this? You look at the element, well, you're supposed to define this map on the kernel, but the element in the kernel is element in this module M double prime, right? So you take this element, well, you can lift this element to the M. Well, the lift is not unique, right? Because there is potentially something that, well, this is not an isomorphism, potentially this V with the bar has some kernel, so, but the lift is unique up to a kernel, right? So you take any lift that you want, right? So then take this lift, and then you can send this lift using map F to some element in the N, right? You get some element here. But since this is commutative, well, you have an element here which is in the kernel of the F prime. So if you go take this lift, send it back here, apply F prime, you'll get 0. This is commutative, so this lift is mapped to some element which is mapped by this map to the 0. So hence, using the exactness, since this is mapped to the 0, there is a lift of this element and unique lift in the N prime. And now what you do, you just, since this is a canonical epimorphism on the co-kernel, well, we just kind of take this element that we obtained and consider its class modulo the image of the F prime. So this is how you get an element in the co-kernel. So there is a little thing that you're supposed to check that, for example, this is well defined, doesn't depend on the lift that you choose, but this choice of a lift is precisely killed by the fact that we, at the end we take the image in the co-kernel. Well, because we take an element in the kernel, right? It is element here which is met by this map to the 0. Yeah, so such proofs, well, it's easier to come up just looking at the blackboard or just looking at the piece of paper than read these books, then read these proofs on the blackboard or read them in the book, I think. So this is what I want to say about the proof, and there will be another statement like this. This is called 5 lemma, and we're going to do this on the seminar. This will be another example of the diagram chase. So, but let's postpone 5 lemma to the seminar. And now I want to do one application of the snake lemma. So proposition let A, B, C be a short exact sequence of chain complexes right? It makes sense to talk about short exact sequences, not just of modules, but of a chain complexes of modules. So then there is long exact sequence of homology. Well, meaning the following, that we can take homology Hn of the complex A. These are mapped to the homology Hn of the complex B. Well, this is not a surprise, since this is a chain map, and any chain map induces a map on the homology. So then this is mapped to the homology Cn of the complex, homology Hn of the complex C. And then there is, again, some connecting homomorphism delta to the homology with the index H, so with the index n-1. And then I just repeat this. There will be H with the index n-1 of B, H n-1 of C, And then you just repeat the construction. So then there will be next connecting homomorphism to the Hn minus 2 of A, etc. So this is called the long exact sequence of homology. Proof. Well, for the proof, I just apply the snake lemma to the following diagram. I look at the An modulo D An plus 1. This is mapped to the Bn modulo D Bn plus 1. This is mapped to the Cn modulo D Cn plus 1. And then there is a map to the Zn A, Zn of B, and Zn of C. Well, that's the diagram that I want to consider. Well, first of all, let's take a pause and tell me, do you have any questions how to get this diagram? Is it clear? Well, by the way, you can even do better. I think you can add, yeah, sure. For the snake lemma, you can add zeros here and here. Actually, you can add zeros everywhere. So is it clear that for any short exact sequence of complexes and any n, we can always construct such diagram of modules? Well, for example, let's look at this part. Why do we have a map here? What's this map? No, clearly, well, just by definition, the map that we're supposed to consider here is just the map induced by the differential in the complex A, right? Because there is nothing else here in this part of the diagram. Well, there is a differential. Well, it's from the. Well, maybe the cycles are with the wrong index. Yeah, the cycles are with the index n minus 1. Sorry. Yeah, so there is a differential from the An to the An minus 1, right? But clearly, if I go to this quotient, the map is still well defined, right? Because d squared is equal to 0. So there is a map on this quotient to the An minus 1. But the image of this map is what we call boundaries, and the boundaries are the submodule in the cycles. So then we have a map to the cycles. So that's an obvious map, right? And why we have, for example, map like this? Well, that is because this is a map induced by this chain map, and also we're using that this chain map commutes with the differential, hence we can induce a map on the quotients. And then the same is true for the other maps here. Well, all the maps are of the same structure. So the interesting question is to, for example, look at these vertical maps and ask what's the kernel and co-kernel to apply the snake lemma. Yeah, so the kernels and co-kernels are precisely the homologies, just with the different indices, right? So well, again, let's for example look at the kernel of this map, right? So what would be the kernel? These are elements in the An which are killed by the differential, right? But we also look at the quotient, so this is modulo the image of the previous map. That's precisely the homology with the index n. Now what are the co-kernel? Well, we take the cycles with the index n plus 1. We already agreed that the image of this map is the boundaries, so the co-kernel is homology with the index n minus 1. So that's exactly what we need to construct this connecting homomorphism. So I think I don't really want to write anything on the blackboard. I think it's easy. Yeah, and this proposition as an exercise, well, supplementary exercise, there's one more thing you can check. I don't want to do this, maybe we do this on the seminar. So the exercise is saying that exercise construction long exact sequence of homology is functorial. Well, meaning the following. If we have two short exact sequences, A, B, and C, so these are exact sequences of complexes, there is another short exact sequence of complexes, everything with the prime. There is a map such that these two squares are commutative. So then you can write one short exact sequence, one long exact sequence for the homology as before. So there is some connecting homomorphism delta here. And you can do the same for the second short exact sequence, so with the primes. And this map of the chain complexes, of course, induce a map on the homology. And the statement is that this construction is functorial precisely means that this square is commutative. So that's a commutative square. So this second connecting homomorphism is also supposed to be called delta prime. And this is for any index n. Okay, so these are just some general words about complexes. Maybe I'll go to the second section, so 4.2, called injective, projective, and injective modules. So this is our next step in the direction of constructing injective and projective resolutions. So, but I want to start with in other definitions, so quite general. So let f from A to B be an additive functor between abelian categories. So then f is called left exact. So I want to introduce the notion of a left exact, right exact functor, and exact functor. It's left exact if for any exact sequence which is exact only on the left. So I have 0, m prime, m double prime. For any exact sequence, if I apply this functor, I'll get an exact sequence. So this is exact. So of course this first exact sequence, this is sequence in the category A, but the last exact sequence is in the category B. So I think this is quite elementary notion of a left exact functor. We just preserve exactness on the left. And there is a dual notion of the right exact functor. Yeah, left exact functors for shortness, I'm going to write lex. So there is a dual notion of the right exact functor I don't want to write the definition. I think it's clear what you're supposed to do. You just, instead of writing 0 here, you write 0 here and say that that the exactness on the right is preserved. And finally, 3, f is called exact if it is left exact and right exact. Or in other words, it's preserving any short exact sequence. Well, we already know actually examples of the such functors. So, example. Now, suppose you have a situation where you have two abelian categories A and B. Тот, который сохраняет прямые суммы. Ну или то же самое, что индуцированный морфизм на хомах – это морфизм абелевых групп. Okay, so suppose we have two abelian categories. Well, you can think about this as I say modules and modules, so it's two different rings. We have two functors, and we know that the f is left adjoint to the functor g. That's the situation I want to consider. Well, now what we can say about the f from the point of view of the exactness. Is f left exact, right exact, maybe exact? Oh, this is left adjoint functor, right? Any left adjoint functor is preserving colimits. An example of a colimit is cokernel. So left adjoint functor is preserving the cokernels, but preserving the cokernels is precisely the condition this is right exact. Is rex and g is lex. So in particular, so the example that we know is the adjunction between the home, tensor product and home. So tensor product is left adjoint. Right, so tensor product is left adjoint, and since this is a left adjoint, this is right exact always. Rex and home is left exact. So, and one of our goals in this second part of the course about the homological algebra is the following. You start with a short exact sequence. For example, for the tensor product, you take a tensor product with some bimodule, right? You get automatically 3 terms. So since this is Rex, you get 3 terms, right? And then, look, I don't know, maybe I write this, m prime, m double prime. So this is right exact. Then you get b tensor m prime, b tensor m, b tensor m double prime. So this is exact by these trivial reasons that we just discussed in this example. But now we can actually take these 3 terms and extend this to the potentially infinite sequence on the left. And then the next terms will be something like tor1 between b and m double prime, then will be tor1 between b and m, etc. So this will be an infinite sequence of tors, and in fact this infinite sequence of tors is just an example of a long sequence of homology for some short exact sequence of complexes. So this is what we're going to do maybe even next week or 2 weeks after this week. And then this is the same you can do for the home. You start with a short exact sequence, you get 3 terms with the homes, and then it will be x1, there will be x2, etc. So these tors and x are examples of the derived functors. But to discuss them, we need the notions of projective, injective resolutions, and flat resolutions. And this is why we need to discuss these notions of the projective, injective modules. Okay. So definition. A module, this could be left module, right module, not important. So a module is called projective let's call this module P. P for projective. It's called projective if now this is quite a long definition, but later I'm going to draw a diagram. It will be much easier on the diagram. So if for any epi m to the n and any map of modules f p to the n, there is a map. So there is a map sigma from p to the m such that beta sigma is f. So on the diagram it looks as follows. You have some epimorphism m, n, so then I write 0 to indicate on the diagram that I have epimorphism or a surjective map of modules. So then what is given to me is the map f from the p to the n, right? So this is map f. And then there is a claim that I can lift this map to the map sigma, which is a map from p to the m. So given epi, so this epi is called beta. I forget to say this. So this is beta. And so the last condition, that the composition of sigma and beta, it just means that this triangle is commutative. Right? So being projective is precisely the same thing that you can take an epimorphism and kind of lift the map of modules along epimorphisms. Well, example, any free is projective. This is an easy example. Well, this is what I want to discuss. I'm asking you a question. Suppose this P, we know that this is a free module. Why there is such a lift? Right, so I can, on the diagram, I can write something like R to the S. Ну, не инициальный. Это же Абелева категория, там инициальный, конечный, это нулевые объекты, нулевые модули. No, here just easy because we have a basis here, right? Right. So we do. These are left to right modules. Well, so here we have a basis, right? So we know that this map F is completely determined by how you take a basic element and you send it somewhere, right? So you then just take the images of the basic elements, and you know that since this is an epimorphism, you can lift them to the M. And you just say by definition that this sigma take a basic element and send this to this lift. Just using the fact that this is free, easy to see this, that there is such a lift. Ну, элемент базиса. Элемент базиса. Тут есть базис. Этот базис отправляется куда-то. То, куда он отправляется, можно поднять в M. Ну, давайте теперь отправлять этот базис, те же самые базисные элементы, в подъемы этих элементов в M. Ну, вот и все. Okay. So it looks like I have 2 minutes, and the next proposition is kind of long, with 5 or 6 or 5 parts. So let's take a break.
Well, I just want to show that for some two maps, F and G, I can send the difference to a non-trivial map. So, for example, if this takes a place when that is not zero, and if that is not zero, then this take a place. And so I have some element.
Is it clear that this is really non-zero?
Я хочу построить такое отображение, что вот у меня на двух различающихся точках разность не зануляется и не зануляется само.
Цель состоит, нужно построить.
Да, я его хочу сейчас построить. Such map H, such that H
Such that this composition
yes,
the difference of two maps applied to the element A is not zero.
So first I wanted to find all elements in B such that and how my map will be defined. If when I send B
I don't understand this. What's here?
порядок B не 0. Порядок B не 0. Ну, то есть...
Это порядок, это порт, да?
Да, это void.
Да, я просто буквы не распознал, да, понятно.
So H send B to 1 over order B. B prime such that and so B prime sent to Wiswin, and all other elements sends to 0. I just need to check what is homomorphism, but
Yeah, I think it will be better if you just write this as one formula, as we usually do. So you're essentially saying that this map H that you want, right?
yes.
So H of, well, let's maybe use C. So H of C. There are 3 options, right? This is if C is equal to B, then what it is?
1 over order B.
So if C is equal to B, and yeah, and also we work on the assumption that the order of B is finite, right?
Yes.
I prefer this notation to do this shortly. So yeah, so this is 1 over the order of C, maybe, where B is equal to C. Now this is L over M B if MC, or maybe I can use B prime, LB, right? And 0 otherwise, right?
Yes, it is under assumption that B has a finite order. In our way, if our map will be defined as and 0 otherwise. So I need to check with this homo and this homo, but so I need to check just and this by definition is oh no. Ну, просто я не хочу писать тут С, потому что это как бы область С на самом деле. Ну, вроде она очевидна, да.
Просто случай за случаем, да, у нас есть 3 случая.
Ну, да.
Всех случаев вроде однородность очевидна. Или честно, правда. Вот в первом случае это очевидно сейчас. Если это самое
Ну, как будто бы, да.
Ну, да, то же самое сейчас.
Ну, если мы умножаем на С, то тут у нас зануляется. Ой, на порядок бета, и тут у нас зануляется. А если на что-то большее, то мы сокращаем на порядок b и получаем что-то меньшее b. Ну да. Тут это вроде тоже понятно. Аддитивность. Ну. I think it's we just need to check it in this way, because in 0 it's clear, and this just by linearity over Q. Я проверил это на B, а тут, ну, вроде по линейности ровно так же делается. Ну, в смысле,
в смысле?
ну, типа, да. Ну, ну, это, да, это лучше написать как B плюс B. I think it can... Ну, на самом деле, потому что вот для нулевого все вроде очевидно, с каким бы случаем мы его не смотрели. Вот. А для этих двух случаев, ну, это вроде по линейности продолжается. Ну, вот что... Нет, ну вот с нулевыми все тривиальные вроде, и вот... Да. Ну, вот с этим вроде все тривиально, как бы мы его не комбинировали. Вот. Ну да.
Хотя там на самом деле, опять же, чисто формально смотреть, первый же случай это частный случай второго случая.
Ну да. В некотором смысле.
Некоторые вполне конкретно.
Ну да.
Сейчас. Или нет? Если это получается или m плюс единица, да? Сейчас, да, я перестал понимать, что это очень хорошо.
Нет, да. Потому что, да, я что делаю? Я как бы беру q-линейную оболочку над B, а само B отправляю в один его порядок.
Нет, я просто не понимаю определение в том случае, что написано там m на n и b.
Ну, B тут должно быть не B на самом деле, а оба с B, то есть один на... Вот так должно быть.
Да, действительно, один частный случай, два.
Ну, да.
На это можно стереть прямо точку.
Ну, да. Ну, вообще тоже, да, можно, на самом деле. Нет. This equation, just from this, by subtracting from each side, ой, не subtracting, тогда we just add to each side m or m multiplied by b. So it sends to порядок B. And it just 1 over c plus 1 over c.
Запишите, пожалуйста, это как-то понятно.
Да, согласен.
Я когда вы встретились формулу, которая там свой чуть левее. Ну, чуть левее, внизу. Я сейчас выпущу не знаю.
Угу. And that's equal to this.
У вас Б вышли какого сорта? А, Б у вас
Б.
просто Б, да? А Б штрих.
Да.
Какой Б пропорция? Да. Да. Нет, так я уже говорю, что это не надо делать просто. Ну, в смысле, надо взять сразу два элемента.
Ну да. Ну, это правда, конечно. Ну, я так понимаю, там просто аналогично делается, потому что тогда если у нас, ну да, тогда я лучше я спешу для общего тогда случая. I multiplied this equation by m, this by m prime, and added. So this sends to and 1 over c. And потому что у нас вот... бля, да, там сумма на самом деле должна быть, я немного тут описался. And I think that it's clear that it's just the sum of two fractions like L prime over M prime and L over M. So, где? M L штрих B? Вот тут M L штрих плюс M штрих L умножить на B. Да, все в скобочках. Но у меня тут немного не уместилось. Могу написать. Не знаю. So we checked additivity, multiplicativity by some integer number. That's homo. It is not zero on this element, so we won. And we need to check this case, but I think it's the same way. Check it. Ладно, я оставлю это. So I think that multiplicativity is clear, and I just need to check that Wait. And so
Почему это отличается от того, что раньше было?
ну, вообще ничем.
Зачем?
Ну, потому что вот это отображение не поделено, когда у нас порядок бесконечный. Но на самом деле, когда порядок бесконечный, нам плюс-минус плевать, куда отправлять какой порядок, потому что мы можем отправлять элементы большего порядка в меньший порядок.
То есть мы сейчас бесконечный случай справа раскрылся.
Ну да, мы просто отправляем его в элемент какой-то нетривиальный. И ну, делаем те же формальные проверки, что все хорошо определено. But I think what's clear that in this case, additivity, it is homothetic because it's just the sum of two fractions like L over M and L prime over M prime. Same way. And so in all cases we constructed such map that it is non-zero on this element, and so it's let's end the proof that the Q over Z is cogenerator.
In this question, we're going to consider short exact sequences of a special kind. This is called split short exact sequences. So short exact sequence 0, M prime, M double prime splits if we can find an isomorphism of the M with a direct sum of the M prime and M double prime such that, well, it's not just an isomorphism of the middle terms, it's actually an isomorphism of short exact sequences. I can write this short exact sequence I can write another short exact sequence which is kind of tautological. Here I just embed M prime as a submodule into the byproduct, or in this case just direct sum of two modules. So here these are the same, and we have an isomorphism, and this isomorphism has to be such that both these squares are commutative. So the exercise is to show that short exact sequence splits if and only if. So let's call this maps I and pi. So if and only if pi has a section. So more precisely means what's the section of a map pi? It's a map, let me call this sigma, that goes in the other direction. And if you consider composition, so you apply sigma, then apply pi. Now this will be a map from the M double prime to the M double prime. This has to be identity on the M double prime. I suggested that we do a little bit more. So try to solve this problem in its usual universal progresses.
So first I need to prove that if this thing splits, that there.
No, if this splits, then exists
Yes.
also sections.
Yeah. Okay. Okay.
А почему ты, ну, как мы поговорили, почему?
Ну, потому что у вас это вот это сечение, это просто вложение m2 штриха в прямой сумме.
Ну да.
Поэтому в одну сторону очевидно,
Окей.
и содержать в другую сторону.
Okay. By the universal property, there is one-on-one morphism.
Примитивность есть. Ну, то есть почему изоморфизм?
Какая селективность?
Ну, в смысле, типа,
Мы
у нас...
хотим M доказать, что изоморфно M штрих плюс M2 штриха. Если-
Нет, но в другую сторону.
Нет, как раз если изоморфно, то секшн очевидно есть, потому что секшн из свойства, собственно, прямой суммы есть вот такая штука, обратная тут, там формула напишется и сократится в ID. Вот. There is map here, one only one by the universal property of this thing.
Why?
No, because we have maps from
To get a map like this, you need to have a map from m to the m double prime, which you have, right? And also a map from m to the m prime, which you don't have at the moment.
У нас we have map from m prime to m and from m double prime to m.
Okay.
So
Вместе
We have-
обратную
да.
сторону стрелка, почему универсальности
да, просто не в ту сторону, а в эту сторону. But сейчас. But this is because this is direct sum, we have a map. This one, A, P. So I want to show that alpha I P is identity M.
А что это докажет, если мы это докажем?
Ну, что у нас вот такая штука, это обратная к вот этой, с одной стороны. Ну и там, что...
Нет, то, что это альфа, обратно к чему мы докажем?
Ну, мы хотим обратную к этой стрелочке.
Да, ID там.
То есть мы хотим, чтобы вот это было, это мы справа, и слева обратно к этой. И вот такое хотим. Сейчас. Окей. In this one, P alpha is P because diagram.
Без никакой.
Нет. Окей. P, so... Что? Потому что P это буквально отображение отсюда, сюда. Сейчас. А в ту ли сторону стрелочка? Нет, не в ту. У нас вот такая стрелочка. Сейчас нет. У нас сигма is equal alpha e because sigma. Ну это прямая сумма. У нас вот стрелочки и вот такие. So this one is equal to sigma pi.
Почему все стрелки единственные из М6
Чего?
Почему единственности стрелки из М2 штука, почему я говорю, что
Ну.
с альфа и то же самое, что сигма? Почему он может не пользоваться?
Ну, потому что у нас есть универсальное свойство этой штуки, что у нас вот есть такая стрелка, тогда вот такая единственная. Что все коммутирует, да. Сейчас. Я в какую-то сторону тут неправильно написал. Сейчас. И сигма, да? Ну да. Ну, тогда у нас, видимо, просто обратно, не то, что я хотел.
Формула себе гипотетически, конечно, пока.
Ну да. И судя по всему, не очень правильно, потому что вот это сигма π, и если ID, то это буквально соморфизм. У нас π сигма ID.
Да, это можно.
Да, так что что-то пошло не так. Сейчас, мы хотим обратную стрелочку, да? Так вот, чтобы не мешалось. Альфа это сигма π. Не очень содержательно, пусть будет. Окей. Сигма π. Ой, сигма p. Пи.
Очень сомнительно, что альфа этому равно.
Ну почему?
То есть,
У нас...
чтобы альфа был изоморфизмом, да, вы сначала поменяете проекцию p, а у нее огромное ядро какое-то. Штрих.
Ну да. Да, сейчас. Ну да, потому что у нас эта штука это из продукта, а у нас свойством копродукта пользуемся. Окей.
У нас у нас есть это другое.
Ну да, просто вот эта композиция, вот эта композиция, она из копродукта, и вот как раз и эта стрелка. Вот эта стрелка, она проекция из продукта, там не коммутирует. Пу-пум. Не очень полезно. Еще мы знаем, что вот такое.
Мне кажется, не хватает одной важной идеи. Если действительно рисовать, как вы начинали сверху вниз, то для этого нужно заработать изображение из этого как штрих.
Угу.
Он действительно существует. Его можно построить. Но просто надо догадаться, как это сделать.
Угу. Затем вам штрих, да?
На самом деле, в этом случае задача установить, она будет несимметричная, да? То есть
Угу.
есть задача у проекции есть сечение. На самом деле можно сформулировать симметричным образом, что у этого положения есть, что называется, ретракция. То есть отображение тоже в другую сторону, так что компонент будет действительно на что эта ретракция всегда существует, как только существует сечение. Надо понять, почему. Если у вас будет такая ретракция, ну понятно, тогда что продолжается само собой.
Ну да.
Сейчас мы не можем заходить с ними. Ну, в смысле, ну там получится просто у нас вот эти тождественные стрелки, некоторые калькуляторы нулевые.
И типа,
Последовательность, что типа
что, что в этой тоже ядро икоида.
0, 0, кукера, 0.
Ну да, полей мезме у нас вот тут ядро, потом вот сюда вот, потом вот сюда, что-то там куда-то. Сейчас, только не в ту сторону, да.
Смотри, кукер, тождественность стрелки из штрих на штрих 0 и кукер. Ну, да, сверху. Так, по-моему,
Что?
ты перепутал порядки.
В смысле, у нас та стрелка.
Да.
Не надо мне тут.
Я все правильно.
Вот типа у нас такая точная последовательность, и вот тут должны быть нули.
Сейчас, а вы знаете, что у вас оба квадрата коммутативные?
Ну, казалось бы. Ну сейчас у нас же тут P не коммутирует в этом квадрате. Ну как возможно? Ну P у нас из продукта, а это как бы для копродукта. Ну ой.
Возможно, нам стоит просто показать, что он коммутирует только
Ну, знаешь.
Зачем нам проверять коммутативность фейс? Нам нужно проверять коммутативность тип, потому что у нас как бы перевернутая картинка с наиклеенной.
Ну у нас все равно последовательность в одну сторону. Ну, как бы перевернутая вот так. Ну да, но нам нужно. У нас последовательность-то тут. Вот с этой стрелкой, а не с этой. Ну не вышло, ну не фартануло. Мы хотим придумать вот такую вот штуку, да? Как-нибудь это назвать, не знаю. Как назвать? Ро? Замечательно.
Вот это вверх? Нет,
Вверх.
не знаю.
Не знаю. Ага. Мы хотим такую, чтобы вот так была единичка. Угу. Пошли вот так. Мы имеем вот такую еще стрелочку. И 2, 1. И мы хотим, чтобы вот как-то вот так, вот так, вот так. Ну да, ладно, факт. Да.
Давайте я дам подсказку. Здесь у нас π и сигма, композиция тождественная.
Ага.
Давайте рассмотрим отображение единицы минус сигма π. Имеет смысл, да? Ну да, это отображение из m и m.
И оно типа, если мы применим π, оно будет нулевым, да.
Значит, оно пропускается через m'.
Угу. Значит, у нас, да, значит, у нас есть вот такое, то есть вот такое.
Ну, надо проверить, что это что правильно.
Ну да, сейчас. Мы хотим, чтобы сигма π q было равно 1, да? Ну, в смысле, у нас вот тут вот. Сейчас, нет, я не то сказал. У нас тут такое отображение, мы хотим вот туда, да?
Давайте туда тоже сотрем.
Да,
Вот это ро, да. И теперь что нужно? Нужно проверить, что если мы, значит, сначала применяем q, потом применяем ро.
Получаем единицу, да.
Вот это надо проверить. Но тогда потом...
Ну, тогда мы получим ретракцию к q, и тогда уже будет понятно, что делать. Потому что у нас будут еще отображения вот такие, и у нас будет еще вот такая единственная стрелочка, и для них тоже все проверится и будет хорошо.
Там на самом деле даже все не надо, потому что если у вас уже сигма есть, мы сейчас построим ро, и просто мы увидим, что все свойства, как у нас в произведении, там просто 4 морфизма и 3 уравнения.
Ну да.
У вас сейчас получится 4 морфизма, 2 уравнения сами собой, само собой.
Ну и третье из точности.
Мы скажем, что это просто произведение и все.
Ну да.
И тогда вот эти всякие универсальные свойства для произведения произведения просто не понадобятся.
Ага, окей. Сейчас,
Потому что надо проверить 2 уравнения.
Нет, в смысле, вот так вроде. Ну, типа у нас, да, π было, сигма было section, а тут типа с другой стороны. Сейчас. Да, у нас 0, поэтому... оно пропускается через ядро.
Там единица на m. Загрузка, которую
Ну, m'. Сейчас, да, руку единичка m-ки. Почему? Да, m', да, действительно. Ну, казалось бы, мы знаем, что у нас про Q это вот 1 минус сигма P, да? Сигма P.
Кстати, заметьте, это есть. Это последнее уравнение.
Да, это... Ну да, это то, что мы хотели как раз, что они сложатся, и не получится.
Да, это получается само собой.
Нам осталось проверить, что вот это осталось проверить, да. Q, ро.
А вот это куро,
Ну, а это просто вот эта штука коммутативная. То есть мы сначала идем вот так, потом вот так. Получается, что вот так.
Это просто определение ро.
Ну да, у нас...
Ро существует, потому что композиция...
У нас вот эта штука пропускается через ядро вот этого отображения. Вот так.
Которая есть тем, что есть.
Угу. Вот, соответственно, хотим вот так, да. М-м.
Да-да-да, мы можем, как мы знаем, что Q это 1 минус сигма умножен на Q справа.
Угу.
Получим, что PQ у нас там будет, да?
Ну да, я как раз вот думал о том, чтобы пройти типа вот так как-то.
Но у тебя получится, что Q...
Ну да, там будет типа Q, ро, Q, это Q минус сигма PQ, вот эта штука 0, это просто Q.
Ну а теперь пользуемся тем, что...
Ну а Q у нас, да, Q у нас моно, да. Действительно, как-то.
Кстати, мораль истории такая, что если делать через универсальные свойства, просто догадаться на отображение единицы минус сигма t, это примерно раз в 10 короче, чем если делать через элементы.
Угу. Ну, то есть можно там гонять элементы как-то и тоже сделать.
Можно с ними через элементы решать.
Угу. Так неинтересно. Да.
So it looks like we don't have enough time for the 5 lemma. I don't know, maybe we actually have 18 minutes, so maybe it's enough time for the 5 lemma. So in the 5 lemma we have diagram with 10 modules and 5 maps. So say M1, M2, M3, M4, M5, and also N1, N2, N3, N4, N5, and there are maps as before. Let's call these maps F1 up to F5. So the rows are exact. All the squares are commutative. So then we can show the following. If F2 and F4 are bijective, F1 is epi, F5 is mono, So then F3 is isomorphism.
То есть в 4 не обязательно объективные как выражение, да?
Ну, здесь речь про модуль идет, поэтому все не важно. Изоморфизм, ну и модуль то же самое. F2 4 изоморфизма, и F1 4 мода, значит, F3 тоже изоморфизм.
А предыдущие задачи чего сигма и у
Потому что чуть-чуть не говорят, они теоретично.
спасибо.
I hope. Okay, so I think this is something like a classical exercise in diagram chasing. So can I erase it? Let us prove that given these conditions, F3 is both surjective and injective. It will be enough to show that this is an isomorphism. So let us start with, I don't know, surjectivity, for example. So suppose we have some element N3, N3 in N big 3. We want to find some M3 which maps to it. So how do we go about this? First we know that N3 maps to some N4 which maps to 0 because the bottom row is exact. Here we have an isomorphism which gives us M4. Okay, I'll draw this like an edge without arrows because it's an arrow in both directions. Okay, so M4 goes to something here, which goes to 0 because the square is commutative. But exactly because F5 is injective, is a monomorphism. We have injection here, so this must be 0 necessarily. Which in turn means that M4 lies in the image of this arrow, and we obtain some M3 here. Now, it's not exactly an answer we want because M3 does not have to map to N3 directly. Generally speaking, M3 has to map to something that maps to N4, which is elements of, which can be written like N3 plus D N2 for some N2 line in N2. Okay? Is this clear? Okay. So now we want to modify M3 by something so that the resulting element maps to N3. Now we obtained, let us look at the image of M3 denoted like this. Now actually we can in this diagram just draw Dn2 plus N3 because M3 maps to it and it maps to N4 because Dn2 maps to 0. Okay, so now here we have N2 which is mapping to, okay, this is not exactly commutative anymore. Okay, we have N2 which maps to Dn2. We obtain M2 which is okay, obtained by going up this arrow. So now let's just look at the element M3, I think minus D M2. What is its image under F3? Well, it's Dn2 plus N3, which is an image of M3 itself, minus the image of Dm2. But here we have a commutative square, Dm2, Dn2. So the image of Dm2 must be Dn2. So this is exactly N3, and the surjectivity is proven. Okay. Well, now let's erase this first. Huh?
Maybe you shouldn't erase this, maybe.
Okay, sorry. Dn2 plus M3 minus Dn2 is equal to M3. Maybe I'll try to fit the diagram here. The diagram for injectivity, I mean. So you can notice that in this proof we used isomorphisms in second and fourth parts and monomorphism in the last part, but we have not yet used the surjectivity of F1, which will be useful for injectivity of F3. So let's start with sum to N4. So N4 must be 0. right? Which in turn means that M4 must be 0, because this is isomorphism. So now M3 lies in the kernel, so it lies in the image necessarily, and we obtain M2, which maps to M3. Use isomorphism again, obtain N2, which maps to 0. Now actually we already know that M3 is in the kernel, but we have to make this claim stronger. We have to show that M2 comes from something. It will give us that M3 is not only in the kernel, it's actually 0, because going to the right 2 times in a row means 0 in an element. So we have to obtain something here. How can we do this? Well, we have N2 which maps to 0. We obtain N1. And now we use exactly the fact that F1 is epi to obtain something. Let's call it M1, that maps to N1. Here we have this arrow because this square must be commutative. So M1 maps to M2, which maps to M3, which means that M3 is necessarily 0. Injectivity is proven.
That's a perfect solution.
Есть solution without прогонять элемент по диаграмме? Just by universal property.
Можно, но это будет непросто. Если вы хотите найти, например, тест, я могу просто указать, где литературе есть. Можете посмотреть Кашевару Шапиру. Там право Кашевара Шапира, там категории пучки книжка. Категории все начнутся. Там будет доказательство 5 лемма, произвольно абелевой категории. Но вот там несколько страниц придется прочитать, всяких разнообразных вычислений. Кашевара Шапира, пучки и категории. Или категории и пучки. Ну что, на этом мы сегодня закончим.